Part 2 of this lesson picks up with this idea of a different number of ways to do this, or to explain this, or to show this. So we have these number sets. Remember, we're using the symbols of, hang on, N, there we go, N and W. That's a terrible W. Let's draw the W first. Z and Q, and then we also are using the symbol Q prime, and together these and these form part of the real numbers. So in number 1, this says to find, or to graph all the x values greater than 4 that are part of the real numbers. So this is the symbol for real numbers in math print. And what I'm going to do with these, I'm always going to put an origin somewhere, but then I'm also just going to stick a 4 so that it's right of 1. And it's a greater than symbol, so I'm going to represent that with an open circle. A closed circle we use to represent greater than or equal to. And really all I need to do is represent everything to the right of 4. So I'm going to shade to the right of 4 and then shade the darkened arrow, indicating this is everything to the right of 4. So I'm starting at 4 and I'm shading everything greater than 4. Number 2 asks us to shade all the x values less than or equal to -1 that are all integers. So I'm going to put a point at 0, I put a little mark at 0 and a mark at -1, and I'm actually including -1. Now, I am not including everything to like this. I'm not going to be shading. What I'm going to be doing is including -1, and then I'm going to skip between -1 and -2, and then skip between -2 and -3, and that's the pattern I'm going to continue. Now, to show that I'm going to continue the pattern, I'm just going to shade an arrow here to show that this pattern will continue for on infinity. But that's shading all all the integers, because integers, remember, are positive, negative whole numbers. Now, moving on to the next one, we're going to shade all the whole numbers greater than -5. Well, I'm going to put a 0 down. -5 is here, but I don't even care about anything into here because whole numbers are only 0, and they're only 0 in the positive integers. So I'm going to start with 0, then 1, and I couldn't put these close, so I've got to keep going. 2, 3, 4, 5. You can put as many or as few as you want to get the pattern going. And I'm going to shade this arrow to show that that continues on forever. 4 is worded just a little bit differently. This is the same as all x such that x is greater than or equal to 3. Now, there's no number set stated. Whenever there's no number set stated, we assume we mean that x is an element of the real numbers. So that's the same thing as this. And if I shade all real numbers greater than or equal to 3, I'm going to put an origin and then a 3 and put a closed circle on the 3, and I really just want all whole numbers greater than that. So we go to the right again and then shade the arrow. And that represents all whole numbers, all real numbers, not all whole numbers, all real numbers greater than or equal to 3, including 3. This is what we call a compound inequality, and this actually means in between. X is in between -2 and +3. When you do compound inequalities like that, you can never ever have the arrows facing different directions. So sometimes Mrs. Manton and I will see things like this, and that doesn't make any sense. These need to be the same direction to describe what's going on. So this is saying that x is bigger than -2 but less than -3. So if I'm going to do that, I'm going to put a -2 down, then an origin, and then +3. And I'm in between, and I'm including -2, but I'm not including 3. And I'm just going to shade everything in between those. And, oh, wait a minute, I can't shade everything in between. This represents integers. So I only want the integers in between -2 and +3. So I'm going to include -2, include -1, include 0, include 1, include 2. Now, you don't have to put an open circle on the 3. In fact, it's a little improper to, because it's just redundant. We're not including 3. I'm going to make this just a little bit darker. Let's do that. There we go. So I don't really want to put the open circle on 3 because I only put the open circle if I'm coming up to and almost including 3, but not quite. Now I'll still put a mark there at 3, but I don't even need to include it at all. Now, this next one is going to be a little bit different, but a little bit the same. This is where I'm going to include -2 and 3 and an origin, and I'm going to include shade here, open circle here, and everything in between, because those are real numbers. That's the whole number line. Now let's try all the rational numbers less than 6. So I'm going to put a 0 here and a 6 here. And I only want the rational numbers. Well, rational numbers, again, are fractions. They're things like 4/5 and 3/5. But if I look in between 4/5 and 3/5, if I make 4/5 become 8/10 and 3/5 become 6/10, I could have this number here. I could have 7/10. But then I could also put one in between these two and one in between those two. And I could keep doing that. These rational numbers are what we call infinitely dense. But they're not the whole number line, because there's also irrational numbers stuck infinitely dense in between them. Basically, I can't just graph rational numbers. I cannot just graph rational numbers. So this is not possible, or not possible to graph. Up here it says, if not possible to graph, stay so. This is not possible to graph. Number 8, all whole numbers that are not natural. Well, there's only one whole number that's not natural, and that is 0. All irrational numbers greater than 2. We have the same problem we just did here. If I can't pull apart the rationals from the irrationals, I cannot graph only irrational numbers greater than 2. There's an infinite number of them, and they're not continuous. There's rational numbers in between them. They're like stuck with the rationals, is a way to think about it. I can't just graph the irrationals without pulling some rationals with it. So I could put a 0 and put a 2 there, but this is still not possible to graph. Now you're going to be tempted to say, well, is that true whenever it says rational or irrational? I mean, I hate saying something's true all the time, but yes, for the most part, you can't just graph rationals and irrationals without pulling apart every real number with it. All whole numbers less than 8. Well, this is very easy. We have only a few whole numbers less than 8. 0 is a whole number less than 8. 1 is. 2 is. 3, 4. Oops, I'm running out of space. Slide that down. 5, 6, and 7. I don't even need to graph 8. I just need less than 8. And there are these 8 whole numbers less than 8 if we include 0, which we should because it's whole numbers. Okay, specify each by roster. This means listing. Like if you have a roster of a team, you're listing them. Natural numbers greater than -4. Well, the first natural number greater than -4 is the first natural number, 1. Then 2. Then 3. Then 4. Then 5. And so on. Integers greater than -5, well, the next integer after -5 is -4, then -3, then -2, then -1, then 0, then 1, and so on. List all the numbers in between -4 and 1, including -4, but not including 1. So it's going to look like that. That's including -4, but not including 1, and they're integers. And finally, this is the same thing as all x such that x is greater than or equal to -3, and x is a real number. And it's impossible to list all real numbers in between something. So this is not possible, because I can't just list real numbers. There's too many of them. There's an infinite number of them. Finally, specified by rule, this means set notation. And there's many answers we can do with these. This I could say, well, this is really just all x such that x is greater than or equal to -4. But I'm going to be very specific and say x is an element of the real numbers. But here in number 16, x is greater than or equal to negative 3, but x is not a real number. X would have to be an integer. I couldn't say whole numbers because I'm including negatives. Now, I could also say all x such that x is greater than negative 4, and x is an element of the integers. I'm going to make this z look more like a z. There we go. But either one is fine. They're both the same set. This one has a few possibilities. I could say 0 is less than or equal to x, which is less than or equal to 4. Put an all x in front, and then say x is an element of, well, I have zeros, so we could say element of the whole numbers. I could also, just for kicks, say x negative 1 is less than x, which is less than 5, and x is an element of the integers, and that would work. See, there's more than one way to do this, but you can't say that x is a natural number because we included 0. So let's look at 18. These are definitely integers. So I'm just going to say negative 3 is less than or equal to x, which is less than or equal to 2. And x is an element of the integers. I could also say all x such that negative 4 is less than x, which is less than 3, and x is an element of the integers. See how those are the same thing? 19, again, there's like 6 different ways to say this one. Let's pick the simplest. 2 is less than or equal to x, which is less than or equal to 6. Those are integers. Those are whole numbers. Those are also natural numbers. You could say any of the 3 of those. You could say whole numbers, you could say integers, and it would really be the same thing. So that's what your homework's going to look like for part of it, and good luck.